Hello, welcome to AQA demola, and today's lesson we're going to be talking about structure and bonding. Specifically, we're going to be focusing on metallic compounds and also your giant covalent lattices. So, going to be a really important lesson. Let's get straight into it. Okay, so we're going to start by talking about metals, right? And your metals are going to be found in groups 1, 2, and 3 of the periodic table, as well as your transition elements. So, see it nicely actually at the bottom, you can see where the metals are. So we've got alkaline metals, alkaline earth metals, transition metals. I don't really count post-transition metals, to be honest, but technically, yes, they are metals. Metalloids you would not have. And then we don't really talk about any other metals in the periodic table. So really, you're talking about aluminium, maybe gallium as well, your transition metals all in the middle here. And then you'll be talking about mainly group 1 and group 2. Yeah? Cool. So scandium is also involved there. Okay, so metals exist as giant metallic lattices, yeah? And this is the general structure that you want to be drawing when you're talking about a giant metallic lattice, yeah? You've got your metal cation, that's a massive circle with a positive, yeah? And depending on the charge, if you're drawing aluminium, make it 3+. If you're drawing calcium, make it 2+, right? And then you have these delocalized electrons that you randomly put around. Remember, the metal cation should be in an ordered sequence. You can see them all in a straight line. The delocalized electrons, put them randomly around whenever you're drawing this and label them. Cool. Now we can talk about what a metallic bond is. It's an electrostatic attraction between metal cations and a sea of delocalized electrons. I cannot stress how important definitions are in your A-level chemistry. Yeah, make sure to learn these definitions because they are not hard to remember. Now, properties of metals. What is really relevant to the course is going to be a very high melting and boiling point because those metallic bonds are strong. So large amount of energies are required to break them, and also that they conduct. These delocalized electrons are free to just move about. Yeah, it's a sea. They just move about between your metal cations. Yeah, so they have the ability to conduct. Okay, and we're also going to talk about giant covalent compounds. Yeah, really on this course, ones that you need to know: boron, carbon, silicon. Those are the only giant covalent structures that we care about. Yeah, and the typical property is that they all have very high melting and boiling points. Yeah, this is because similar reasoning, covalent bonds are very strong and require a large amount of energies to break. Other bit, and to be honest, it was more of a concern for your GCSEs anyway, but we do need to talk about allotropes just a bit. Different forms of the same element, and on this course, mainly all we really need to care about is graphene, graphite, and diamond. Yeah. The main thing we care about is this. Yeah. So in diamond, if we look at the central carbon, right, we can see it's such a 1, 2, 3, 4 other carbons. Right. Stay with me. If we're covalently bonded to 4 other carbons, and I know carbon, yeah, has 4 electrons in the outer shell. There are no delocalized electrons. There's no free electrons, yeah. So this cannot conduct electricity because all of those electrons are localized and bonding. That's another bit to add, that the electrons are localized and bonding. So that's not in the notes. Graphite is a bit of a different story, yeah. So graphite, you can see here, 1, 2, 3. So the carbon are attached to 3 other carbons. So there's a 4th electron that is not involved in bonding. That's delocalized, yeah. So it's delocalized. Then they can move between these layers. You can see these van der Waals forces. That's why graphite, they can slide over each other. Yes. So you can see here, van der Waals forces between the layers. Your electrons can go through because there's another delocalized one. Yeah. Coolio. Graphene is just a single street of graphite. I don't think you really need to know much about it except for what it might be useful for. Wires, sports equipment, so much more. Just look it up. And also conductive because again, that's a delocalized electron. Something important to mention is about the trend along the period. So period 2 and period 3. You can see at the start, up until group 4, we've got our giant structures, yeah? Giant metallic lattices, giant covalent lattices, yeah? Know that. Cool. Giant structures, obviously more bonding or more strong bonds, so we need more energy to overcome. Then after this, we have the simple molecules. Really, really easy. And I wouldn't necessarily take this diagram as gospel, but this is the kind of trend you expect to see, that it starts going up until you hit period 4. Group 4, and then it comes down. Yeah. Period 3, probably more likely to get asked about, but again, it's a similar story. It's a very similar story. Yeah. I don't want to spend too much time on this, but just know that. And the only reason why you're seeing, like, for example, maybe a bit of a variation here is because sulfur exists as S8 and phosphorus exists as P4. So if we have more electrons, it will have more electrons than like chlorine and argon. And chlorine even has more than argon because it exists as CO2. So as more electrons, it will form stronger van der Waals forces. Yeah, Hope that makes sense. Okay, if I'm correct, this is going to be a bit of a short video, but question time. So you got the first question. This is really, application is really where you're going to get the most marks. So explain in terms of melting points in terms of bonding and structure, and then also you're filling out this table and then explaining those two statements below. So I'll give you time and then we'll get into the answer. Okay, to be honest, it was quite the squeeze trying to get all of this in, but I just care about what each of these are. So aluminium here, you should know giant metallic. Yeah, I explained giant metallic about strong metallic bonds. You've described what a metallic bond is there, and you can say a lot of energy is needed to break them. Yeah, cool. Similar story when we talk about silicon, giant covalent, right? So they've mentioned about bonding with 4 other silicon atoms. That's fine. What I really need is the strong bonds. I need to define what a covalent bond is, and you can see energy is needed to break them. That tends to be the strongest one. Yeah. Phosphorus and sulfur, both of them simple compounds, yeah? So simple molecules. Yes, there are strong covalent bonds between the atoms, fine. But the main relevant thing is that the induced dipole or the van der Waals forces are weak, yeah? So there's not much energy needed to overcome. Then, this is the point that we just made in the previous one. S8 is over P4 because there's more electrons. So those van der Waals are stronger. Cool. Next question was to fill out that table, I believe. Let me check. Yeah, to complete that table. So we have the headings, right? And then you just need to name them. Yeah. So I think it's here. Yeah. Giant ionic, giant metallic, giant covalent, simple molecule. Yeah, you do need to know that. So silicon, giant covalent, phosphorus trichloride, simple molecule, aluminum metal, and then magnesium sulfide ionic. Yep. Cool. And then in terms of the statements that we had, MgS has ionic bonds, PCl3 has intermolecular forces. We need more energy to break ionic bonds compared to the van der Waals force. Yeah, so that's why we're going to have that difference there. Conductivity. Remember we said metals have delocalized electrons. Your giant covalent compounds like silicon do not. Yeah, and because they don't, that means they cannot conduct. Okay, you may have gotten a bit of a sneak peek actually to the A-star tips, but we said it nonetheless. What is really good to do in this topic? Well, identify what type of structure a compound has. Yeah, if you can look at a compound and say this is a simple molecule, this is a giant covalent lattice, you're already half of the way through. Yeah, then that will make it a little easier to the second point to describe the properties. Yeah, it's all good telling me that giant covalent compounds have a high melting boiling point. Please explain to me why. Yeah, because those bonds are so strong and hard to break. Also, focus on the trends along the period. I'd say specifically period 3. They do love a bit of a question about comparison along the trend, especially in this topic. What do we not do? Don't confuse simple molecules with giant structures. I've seen it happen before. Please do not do that. Allotropes, very easy to forget because I'll be very real. I barely ever remember being asked about them. And thankfully, it's only graphite, graphene, diamond you need to know. You don't need to know about like Buckminster, fullerene, whatever. Just learn those 3. Yeah, it doesn't take too long. Very much good to know just in case. Diagrams, label them, literally. I think it's normally a marking exam to label a diagram, so make sure that you do that if you're asked to draw one. And then as well, with the giant metallic compounds, it's very, very important that when you're drawing it, you draw it correct. Yeah, so draw the electrons randomly about. It doesn't even need to be like, let me do it in pencil. It doesn't even need to be like one of these. It can literally just be a dot. And if you just do from that dot, say it's an electron, the examiner's going to allow it. Yeah. And then make sure as well that it's ordered, the metallic lattice. Make sure that the actual metal cations are quite ordered. That's what they're really looking for. Okay, I hope that video was quite helpful. If you have any questions at all, drop it in the comments. I'll do my best to answer them. If you enjoyed the video, found it useful, please like and subscribe to the channel. We are actually getting quite close to 500 subscribers, so that would be amazing. We've got the TikTok and the Instagram, both at demola. Drop us a follow for me, please, and I'll catch you in the next one. Bye for now.